Hello, this is problem set number 3, problem 3. When a quantity of monatomic ideal gas expands at a constant pressure of 4 times 10 to the 4th pascals, the volume of the gas increases from 2 times 10 to the minus 3 cubic meters to 8 times 10 to the minus 3 cubic meters. What is the change in the internal energy of the gas? Okay, well, what is internal energy? Internal energy is the same as the change in thermal energy, right? So that's another way of saying internal energy. Okay, and over here to the right of the page, I just have some free info that I think is useful for solving homework problems and answering tests. So if you guys can have a cheat sheet to the test, I highly recommend that you guys write this down somewhere so you know it. Okay, the first one is from chapter 18, section 4, and that's that the molar heat capacity for a monatomic gas is equal to 3 over 2R. That's this guy right here. Okay, this guy. 3 over 2 times the constant R, right? The second info that is useful is that the constant R has a value of 8.31 joules over mole times Kelvin. The third info that's useful is that pascals, the unit, is the same as the unit kilograms over meters times second squared. So whenever you have the unit pascals, you could also just erase the unit pascals and use the unit kilogram over meter times second squared instead, and that would be equivalent units. Same thing with number 4, joules. The unit joules is the same as the unit kilogram times meter squared over second squared. In chapter 19, section 7, that is internal energy and first law of thermo, we are given the information that the molar heat capacity for a constant volume, CV, capital C subscript V, is equal to the molar heat capacity for constant pressure, C subscript, capital C subscript P, minus the constant R, okay? And also from chapter 19, section 4, there are 3 equations that are very important that you guys should know and have in your cheat sheet. The first is a first law. Equation number 1 is the first law of thermodynamics, and that is that the change in thermal energy, also known as internal energy, right, is equal to the heat transferred to the system minus the work done by the system. Okay. The second equation is that the change in thermal energy is equal to the number of moles times the molar heat capacity for constant volume times the change in temperature, okay? And that is an equation you can use for all processes, meaning isothermal process, which is constant temperature, isobaric process, which is constant pressure, isochoric process, which is constant volume. For all those processes, this equation applies, so you can use this. Now, this third equation, you can only use this for an isobaric process when the process has a constant pressure, like our problem here, constant pressure. And you can use this, that is equation that says heat transferred to the system, Q, is equal to the number of moles times capital C subscript P, which is the molar heat capacity for constant pressure, multiplied by delta T, which is a change in temperature, right? Okay. And lastly, some interesting info that I only found out about yesterday. So when you have the ideal gas law, PV equals nRT, okay? And I wanted to put this delta outside of it for the whole equation. So I did not know that this delta actually works like a derivative right here. So you could remove the constant out. So for example, on the right side of the equation, delta PV, in this case, remember, pressure is constant in this problem. So actually that would be, I can remove P to the outside of the delta. So it would be P times delta V, right? So I thought that was interesting. And for the right side of the equation, nRT, because I have a specific quantity of gas and that doesn't change. Also R doesn't change because that's a gas constant. Temperature, however, changes. So on the right side of the equation, I could bring out the N and R. And so it would be on the right side of the equation, it'd be N times R times delta T. So that was very interesting info that will help us on this homework a lot. Okay. All right. So let's write down our givens for this problem. What do we know? We know that we're dealing with a monatomic ideal gas. So monatomic ideal gas. We know that the gas expands at a constant pressure. So that means it's an isobaric process, right? And that is just a really weird way of saying that the process from state 1 to state 2, or the initial state to the final state, had constant pressure. Pressure did not change throughout in the path between states, okay? What else do we know? Our initial volume is equal to 2 times 10 to the minus 3 cubic meters. Our final volume is equal to 8 times 10 to the minus 3 cubic meters. I guess 2.00 and 8.00, but I'm not going to rewrite that. I'll just, that's 2 times 10 to the minus 3 cubic meters. And we are looking for the change in internal energy of the gas. And that's just another word for saying we are looking for the change in thermal energy, right? Okay. Let's draw that out. What does that look like in a PV diagram? So that's our volume line, and this is our pressure line. Okay. I know that I have constant pressure, so this will be my constant pressure, where, oh, I didn't write that down, but I have constant pressure, so P1 is the same as the final P, initial P is equal to final P, and we'll call that P, and that is 4.00 times 10 to the 4th Pascal, okay? That's also a given. So these are my givens. All right, so my pressure doesn't change, and that's right here. That's 4 times 10 to the 4th pascals. My initial volume is V1, which is 2 times 10 to the minus 3 cubic meters, right? And I have here my V2, which is my final volume at 8 times 10 to the minus 3 cubic meters. All right. What do I know about the PV diagram? If this was my initial state right here at V1 and P1, which is just P because pressure is constant, and this is my final state, state 2 at P2, V2, which is just P because P is constant, and at volume 2, right? So my path between states looks like that. That's a horizontal straight line, right? Going from left to right. So it expands, the gas expands, which is what the problem said. What do we know? So we know that the area under that curve, this area, the area of the rectangle, is equal to work. Okay? And now, there are actually two ways to solve for the change in internal energy of the gas, or the change in thermal energy of the gas, right? And I'll write those two ways down, and then I will solve it one way and then solve the other way, okay? So the first way is that the change in internal energy is equal to Q, which is heat transferred by the system, heat transferred into the system, right? Is minus the work done by the system. Okay? So change in thermal energy, or change in internal energy, is equal to heat transferred to the system minus work done by the system. So that's the first way we can solve this. All right? And the second way we can solve this is the equation right here, equation 2. So the first way was we use equation 1, right, from chapter 19, section 4. And the second way is to use this equation, which we can use for all processes, also from chapter 19, section 4. So that is the change in thermal energy is equal to the number of moles, N, times the molar heat capacity, right, for constant volume, multiplied by change in temperature. Okay? So these are the two ways to solve the problem. Method 1 to solve problem. And this is method number 2, okay? And I'll do both methods. I'm going to start off with method number 1, and then I'll do method number 2. If you guys just want to watch method number 2, then just fast forward this video and skip past method number 1. And if you want to see both, which is kind of nice, then stick around and watch it. But I'll do both methods. All right? Okay, let's start with method number 1. All right. Change in thermal energy equals heat transferred to the system. Whoa, how do I get rid of that? Yeah, okay. Minus work done by the system. Okay. So what is another way to write Q, or heat transferred to the system? It's right here. For an isobaric process, only for constant temperature, only for constant pressure, I could use this equation in equation 3, okay? So I'm gonna substitute Q for N times molar heat capacity for constant pressure times delta T, okay? Minus work done by the system. And what is my work done by the system? Again, remember, it's this area right here under the curve, right? And that's very easy to calculate. It's just a rectangle. So the work done by the system is the height, which is P, right? That's a constant pressure, 4 times 10 to the 4th Pascal, multiplied by my base, which is the change in volume, or delta V, right? That's just V2 minus V1. Okay? So that's how I'm going to solve it. But I don't know what is my CP right here, right? I don't know what my whole molar heat capacity for constant pressure is. So how can I keep going with this method if I don't know the molar heat capacity for constant pressure? Yeah, I don't know the molar heat capacity for constant pressure, but chapter 19, section 7 has an equation that shows the relationship between molar heat capacity for constant volume, or capital C subscript V, and molar heat capacity for constant pressure, which is capital C subscript P. Right? And that's this equation right here. So using this equation, I will substitute Cp, right? So I would get N, and instead of writing Cp, I would write times Cv minus R, molar heat capacity for constant pressure minus R, times delta T, right? Because that's delta T from here. But Cp I substitute for Cv minus R, right? That's all I did. Okay, minus my given pressure and the difference in my volume, which is given in the problem. Okay. Unfortunately, I also wasn't given Cv, right? At least a value for Cv. But in chapter 18, section 4, we know that the molar heat capacity, right, this guy Cv, for monatomic gases, which is what we're dealing with the monatomic ideal gas, is equal to 3 over 2R. Okay, so I'm going to substitute Cv with 3 over 2R. Okay, so equals N times 3 over 2R, that is just Cv, okay? I substituted this for this due to this equation from chapter 18, section 4. Okay, and minus R, I'm going to say minus 2 over 2R, right? Because 2 over 2 is just 1R, which is what we have, times delta T minus pressure times change in volume. Okay, so this will give me N, and 3 minus 2 means I have times 1/2 R times delta T minus, I think I've made a mistake. Okay, so Cp should be Cv plus R. Okay, I'm sorry. Right here, right? Cp, we would have to transfer R, negative R to the other side, so it would be Cv plus R. So, okay, Cv plus R, Cv plus R. So, I would get 5 over 3 plus 2 is 5, right? So I would get 5N times 5 over 2R times delta T minus pressure and change in volume. Okay? So what do I know here? I know N, right? That was given to me. I'm sorry, I do not know N. I do not know N. I know R. I don't know delta T. I know the pressure and I know delta V. So that is going to be kind of tough. And that's where this random equation right here, or this random info, comes in handy, right? Because I have a delta T here on this side of the equation, right? So again, like I said, the delta works like a derivative where you could take constants out. So let's use a color that we haven't used, like bright blue. So if we have the ideal gas law, PV equals nRT, yeah? And I want to take the delta of the whole thing, right? So this becomes delta P times V is equal to delta of nRT. Yeah. And again, in this problem, it's stated that pressure is constant, right? Constant pressure. So P1 equals P2, which is, we'll call P. And again, this works like a derivative. I could take the constants out. So since my pressure is constant, it becomes P delta V, because volume is not constant, it changes from V1 to V2, right? Is equal to, N is constant, I just have a quantity of monatomic ideal gas, so N can come out. R is a constant, and temperature changes, so nR delta T, okay? So this is, I can do this, again, because of this random fact right here, that works like a derivative. Okay. So if I move the constant from the top line out, so to the left, it would become 5 over 2 times N times R times delta T minus pressure times delta V, right? Oh, look. nR delta T, nR delta T. So I'm going to substitute nR delta T with P delta V, okay? So then that would become equals 5 over 2 P delta V minus P delta V, okay? What a coincidence. I know pressure and I know the change in volume that was given in the problem. So now I can solve for my change in thermal energy. Okay, so 5 over 2 minus, let's say this is 2 over 2 because that's just 1, is 3 over 2 pressure times change in volume. Okay, and that was given in the problem, so that's 3 over 2 times pressure in the problem that was given as 4.00 times 10 to the 4th Pascal, right? And times a change in volume, which is 8.00 times 10 to the minus 3 cubic meters, minus the initial volume was 2.00 times 10 to the 3 cubic meters. Okay. If I plug that in my calculator, that would be equal to 360 pascals times ATM. Or sorry, not ATM, pascals times cubic meters. All right. That is a weird unit because we don't really use pascals times cubic meters. But in this free info sheet that I wish I had, which we have for free, so we should write it down. We have pascals. That unit can be changed to kilograms over meter times second squared, right? So let's do that. So is equal to 360 pascals is kilograms over meter times second squared. And then we bring down this other times this quantity of cubic meter, right? So we could cancel this meter out and this becomes to the second power. And wow, would you believe we've got ourselves a joule, because kilogram meter squared over second squared is the same as a joule right here, right? They're equivalent units. So our final answer would be our change in thermal energy, also known as change in internal energy, is equal to 360 joules. Okay? There you go. All right, so that's the first method of solving that. And the second method of solving it is, which we will do here, okay? The change in thermal energy is also equal to the number of moles times the molar heat capacity at constant volume, C subscript V, capital C subscript V, times the temperature difference, delta T, okay? So, again, what is another way of writing the molar heat capacity for constant volume, CV? We could write it as 3 over 2R, right? So let's do that. So this is equal to N times 3 over 2R times delta T, okay? Again, I'm going to move my constant to the leftmost side. So that's 3 over 2 N R delta T. Okay, that's the same thing we saw earlier. We've got NR delta T. And again, due to this random fact right here that the delta works like a derivative, we can, we found out from this part, right? Because it works like a derivative and we took the constants out, that NR delta T is equal to P times delta V. Oops, NR delta T. Okay, so we're going to substitute this NR delta T with this, okay? P times delta V. Okay, so that becomes 3 over 2 P times delta V. And again, we were given our constant pressure, P, and our change in volume, V2 and V1, so we can solve for delta V. Okay, and let's do that. Oh, look, we already did it earlier. Okay, there you go. So same thing, you just plug and chug and you would get that the change in thermal energy is equal to 360 joules. So these are the two ways of solving this problem, okay? Hope that helped.